get that going. Okay. Okay, so the group activity should now be available. Upcoming deadlines, 3 content videos for tomorrow. Friday is homework number 2. There are 3 multi-parts and 1 supplementary question. And a week from today is the first group activity. There is an error in the properties of solids quiz again, and since some people have already taken it, I can't upload a different version that corrects the error again. There is a question about a liquid not having a defined shape, and the correct answer is that it's not a defined shape because it adopts the shape of its container. The quiz, for some reason, I clicked on the wrong thing, and it's expecting me to put in that it's like dividing by zeros undefined, and so it's mathematically not meaningful. Now, there are 2 similar questions. The first one's about gases. The second one's about liquids. The gas one's right. The liquids one, you have to enter the incorrect answer, like dividing by zeros undefined. Okay, I apologize for that. I'm going to introduce an extra debugging step in my quizzes going forward to try to avoid this happening anymore. Okay. My office hours have been posted. This is a full list of all of the synchronous stuff that is happening, including my office hours, the LA sessions, and the classes. This is pinned in Piazza, including the links to be able to get into them. Do please feel free to drop into my office hours anytime. Just drop in and ask questions. You don't need to make an appointment to do so. I've not had anybody drop into them yet, so you will have a very short waiting time as you come in and try to ask me for some help. Okay, any logistical things we need to talk about before we start getting into the material? Okay, let us take a look at some of the muddiest points we have. So they seem to fall into 2 main categories. There are the phase diagrams kinds of questions, and then there are the crystal structures, properties of solids kinds of questions. So I'm going to do them in that kind of order. So the first one that came up was about, I believe, the supplementary question for the homework this week is asking about drawing and labeling the path of a sample on a phase diagram, and then drawing the cooling curves, and not fully understanding what that means. So let's take a look. We will start by drawing a phase diagram, so we have something to work with. And so if this is temperature and this is pressure, a typical phase diagram might look something sort of like this. So let's just do some orientation here. Where is going to be the gaseous region? So I see somebody pointing, which direction are you pointing to? The top left, so you think the gaseous region is going to be here. So that the gaseous region then would be at high pressure and low temperature. Does that make sense? Okay. So where do we think instead? Yes. Over here, right. So this will be the gas region. We're at high temperature and low pressure. Okay. So what do we think this region is going to be? Liquid. And what is this region going to be? The solid. Okay, so the question is asking, starting from a given point, and so then you have to be able to identify that point, and most of those points are in relation to the critical point and to the triple point. So starting at a high temperature, above the critical point. So that would mean you're going to start somewhere like this. Maintaining the pressure and then cooling the sample. All that means is You're going to keep it at a constant pressure, and you're going to cool the sample until you're well into the solid region. That's what I mean by tracing the path of the sample. It is a line that is illustrating where the sample is in its pressure temperature, on the pressure temperature axis as you take the sample and you are cooling it. And it's asking you to do that for 4 different samples, if I remember correctly. So you're going to have one that's going to be here, and you'll have a B, a C, and a D. You're going to do something similar. And then it wants you to draw a cooling curve for each of those. And so you're going to have a cooling curve, which is going to be with time. So you are removing a certain amount of heat per unit time, and it's going to be temperature. What you're going to do is you're going to start at a given temperature. So you're going to start here, whatever that temperature is. You're going to be cooling down. Okay? At some point, you're going to get to the line that is crossed out. Something's going to happen at that line, which means that it's going to do something different at that point. Then once you pass that line, you're going to continue to cool. Okay? So you're going to have one of these plots for each one of the lines that you draw here. That general idea makes some sense? So there are examples of these curves that are done in the cooling curve or maybe heating curve video, but the heating curve and the cooling curve are just the opposites, depending on whether you're starting at the low temperature or the high temperature. There's an example in there that talks you through the general process. Now, I'm not in this case going to be grading you on whether you get the slopes right or how long various lines need to be. But I do want to have the places where things change. So you go from one behavior to a different behavior here. That's going to be happening at a particular temperature. If on the next line that same transition is happening at a lower temperature, then you need to make sure that where that happens is at a lower temperature relative to where you had it over here. Does that make some sense? Okay, so that's what I'm asking for this plot, and the cooling curves and phase diagrams video walks you through the various steps. Okay. Any clarifications or questions people have on this? Okay. So let's stay with phase diagram kinds of things. So the video said the only difference between the phase diagrams of water and carbon dioxide are the melting point, but the plots look completely different. What's going on with that? Well, I went back and checked, and the video doesn't say that that's the only difference. It says that there is one significant difference that is qualitatively different between the two. They are definitely quantitatively different because the temperatures at which things happen are different for the two different species. Absolutely. But there is one particular thing that is qualitatively different. So we have one phase diagram that's shown here. I'll draw another phase diagram down here, like this. What's the qualitative difference between these two? Point at which it starts to solid, okay? All right, the slope of this line versus the slope of this line. In this case, it's leaning to the right. In this case, it's leaning to the left. So that is because for most substances, the solid is more dense, is more compact than the liquid. And so if you start here and increase the pressure at a certain temperature, By compressing it, you're forcing it into that solid arrangement. And so under pressure, you can induce a phase change to make it become a solid from a liquid. In this case, however, because it's going the other way, you add pressure, and that induces a transition from the solid to the liquid. Because in this case, for water, the liquid state is more compact than the solid state. Water has an unusually ordered and unusually open crystal structure. So that is a key difference. Now, there are other differences because this is at a different temperature and pressure. This is at a different temperature and pressure. Where they are specifically is different. But the general shape is the same with this exception of which direction that lines up. That makes some sense? Okay. Now, let's talk about this one down here. So I mentioned in the video that there's a myth that ice skating happens because of the phenomenon I just described. The idea that the pressure of the skater being applied through the skates causes the ice to melt, and that is why we are able to slide in slippery fashion across the surface of ice. That is a myth. So the question is, what's actually happened? So, and this is an excellent thing to go into. So let's look at some information and try to understand a bit of what's going on. So the temperature of the ice in an ice rink is usually set to be around 4.4 degrees. I'm sorry, that should be negative 4.4 degrees C. Yes. So apologize. Thank you. So negative 4.4 degrees C. We can find the slope of that line on the phase diagram. For every additional atmospheric pressure that's applied, the melting point of ice decreases by 0.0072 degrees C. So that means, since we know what the temperature is, we should be able to calculate how much pressure we would have to apply in order to have the melting point drop that far. All you do is you take 4.4 degrees C, divide it by 0.0072, and that tells you how many atmospheres of pressure are required. You do that, and you get 611 atmospheres of pressure. Just a lot of pressure. Now let's figure out how much pressure is being applied by an ice skater. So the contact area of a pair of ice skates is typically around 0.003 square meters. So you just take the width of the ice skate times the length of the ice skate times 2, since there are 2 skates, and that's roughly what you get. Let's assume we've got a kid skating, because we know that children are able to skate. So we have somebody that's about 100 pounds, which is 45.4 kilograms, which is, when you go from mass to pressure, you multiply the mass by the acceleration due to gravity, 9.8 meters per second squared, to get the force that is being applied, which is 445 newtons. Now, pressure is force per unit area. So you take 445 newtons divided by our area, 0.003, to determine the pressure that's being applied. So 445 divided by 0.003 gives us a value of 148,000. Well, newtons per square meter is a Pascal. When we convert that to atmospheres, that's 1.46 atmospheres. Compare that to the 611 we need in order to melt the ice by this, at this temperature. So we are 2.5 orders of magnitude off from this being the correct explanation. So it is a myth that the ice is melting because of the pressure from the ice skates. What's actually happening? The surface of the ice isn't solid in the same way that the bulk of the ice is. And so for the same reason that was explained in the properties of liquids video about surface tension. Because the hydrogen bonds are so strong, the hydrogen bonds in the bulk can have all four from the water, 2 where it's a donor, 2 where it's an acceptor. But on the surface, at least one of those is pointing out into empty space. This would be a frustrated hydrogen bond because there's nothing for it to bond to. So the surface molecules of water tend to, both in liquid and in the solid phase, tend to rearrange in a kind of disordered way to trying to maximize how many hydrogen bonds you get in that phase. And so the surface of ice has a few layers thick that is disordered and somewhat mobile. So there's a very thin layer that is much more liquid-like. So that's the real explanation. And you'll notice that this picture is from a paper only 4 years ago, a research paper only 4 years ago. So this is something that is still being studied and still being tried to be understood right now. Okay. Any questions on any of this, how this works? Okay. All right. How does a liquid freeze while simultaneously staying at the same temperature? Okay, that's an excellent question. That's talking about these cooling curves or heating curves. So let's suppose that we have a sample of liquid water at some temperature, and we are cooling it until we reach the freezing point. Okay, so if this here is the freezing point, the temperature at which it freezes, we cool at roughly a straight line down here. Now, what determines the slope of this curve to that point? The volume, how much you have, certainly, that's going to be part of it. How fast you're taking the heat out. And also an intrinsic property of water. Anybody remember what that is? Specific heat, right? So the heat capacity of the sample. So that, remember what the heat capacity is back from thermochemistry in 111. Heat capacity is the amount of energy it takes to change the temperature of the sample by 1 degree. Okay. And so if that's a relatively constant value for a phase, then you're going to end up with a straight line if you're taking heat away at a constant rate. Once you reach the freezing point, you start to have something happening that is essentially a chemical reaction. So your H2O liquid in equilibrium with H2O solid. Now, we haven't really gotten into equilibrium yet. The idea of an equilibrium is that the reaction is going both directions at the same time. So it's called a dynamic equilibrium. The dynamic equilibrium is such that the amount that you have on each side of this is determines, well, let me back up. Let me just cancel that thought. We're going to skip that. Okay. So what's happening at this point is we now start to generate a little bit of ice. Is this process here going in that direction? Do you expect that to be endothermic or exothermic? Yes, exothermic. That's correct. Why does that make sense? Releasing heat. What's the other point? Okay. Okay. Right. So it's releasing heat, and what's happening is that the liquid state has more energy in it than the solid state. So if you're going from liquid to solid, you are going down in energy, within the system, which means that energy has to go somewhere. It's being released. Okay? So while that is happening, while you are transitioning from liquid to solid, and you have the system set up in a way where you are constantly taking out a certain amount of heat over per unit time, then what's happening is that the amount of heat that's being released is coming from the phase transition, not from a change of temperature. So for a while, you start at this point with 0 solid. You stay at the same temperature for a while. You get somewhere along here, 50% of it is liquid, 50% of it is solid, and then you get to a point that is 100% solid. Because the heat that is being removed is driving the phase transition, not a change in temperature at that point. Once you get to 100%, it's now all solid. This reaction can't happen anymore. What do you think is going to happen next? It'll start getting colder again. It'll start going down, and you are now continuing to remove heat, remove energy from the system, will start to once again cause a decrease in the temperature. Okay, does that make some sense? So, and this slope here is likely to be different from that slope because the heat capacity of ice is going to be different from the heat capacity of liquid water. Yes?
So that it will decrease in temperature not reaching the phase change. Once it starts to go through phase change, complete the phase change, that won't be constant. Once it reaches the solid,
until there's some other phase change, if there is one. Yes, that is absolutely correct. So for people in the chat, I will repeat that. So the student here present was verifying his understanding. What you have is a decrease, a linear decrease in temperature until you reach the phase change. You then have a constant temperature while the phase change is happening. Once the phase change is done, you then have a new decrease in temperature starting out that will then continue until the next phase change occurs. Right, and if you're making a heat diagram, it's the same thing, just in reverse. You just flip the x-axis, and you're starting at a low temperature and going to a high temperature. Exactly the same thing. And there's no difference in behavior for whatever the phase change is. So if it's liquid to gas versus solid to liquid, the same general behavior is what's going on in just a second. Any other clarifying questions? Okay. So I believe we are now ready to move on to questions of solids and crystal structures and this sort of thing. Okay. The most popular question in this was about packing efficiency. What does it mean and how do you calculate it? Why is it important to that? Okay. So I should have brought a bunch of spheres. I'm going to put here. Okay. Okay, so if we look at a picture of some stacked spheres, I guess we'll look at this one. I have a picture not come up. Not showing up. All right, here we go. If we look at the packing of spheres that we have here, it's hopefully pretty clear that there are some holes in between. Oh, it's not showing up on this one. Thank you. I got it fixed for the chat, but I forgot to do it for the overhead. Okay. So hopefully you can see here that there are holes in between where the spheres are resting. So if you imagine taking a bunch of these spheres, dumping them into a beaker, and then pouring in some water, the water would have someplace to go because it would fill in the space in between the spheres. Even if the spheres are packed together as closely as possible, there's still space there. Packing efficiency is trying to quantify that idea. It's trying to quantify, if you do that, what fraction of the space is taken up by the spheres and what fraction of the space is taken up by the water that you pour in. That's the idea of packing efficiency. So what we can do is, let me put this back. Let's start by looking at simple cubic. All right, simple cubic is something like this, and there is a sphere centered on each of the corners. If we are to, if we're only going to look at the unit cell itself, not how the atoms are extending out beyond it, then what we would do is draw in the slices of the spheres that are at the corners. Okay? So, in this simple cubic arrangement, this distance right here is a radius of the sphere. And this distance right here is a radius of the sphere. Does everybody see that? Because in this arrangement, the corners are touching each other along the edges. So what is the length of side of this cube? 2r. Okay. So if it's a cube, what is the volume of that cube? 2r, the quantity cubed. Okay. Or 8r cubed. Thank you. There we go. Is that better? Okay. So this is the volume of the cube. Now, if we look at the portion of the cube that the spheres are taking up, the easiest way to do that is for us to count how many spheres there are in the cube. Well, there are parts of 8 of them, right? Because there's one at each of the 8 corners. So it's going to be 8 times something. What fraction of the sphere is represented by each of these corners? 1/8. Okay. So that means that we have 8/8 of a sphere, or 1 whole sphere. Now, we know we have R already. What is the volume of a sphere? Anybody remember that formula? 4/3 pi r cubed. Yep. So the volume of the sphere is, if I write it correctly, 4/3 pi r cubed. So if we take the volume of the sphere divided by the volume of the cube, that tells us the fraction of the space that is taken up by the spheres. Because the cube is everything. It's the sphere plus the water, right, in the analogy I was giving. Yes? Is the fraction of the space that is taken up by the spheres. So our packing density, or packing efficiency, is going to be 4/3 pi r cubed over 8 r cubed. And so somebody with a calculator, the r cubes cancel. We can have the 4 cancel with this, so it's a 2, right? And we have the denominator, and we end up with pi over 6. I think I did that right. Can someone calculate for me what pi over 6 is? Okay, so it's around 0.52. So 52% packing efficiency. 52% of the space is taken up by the spheres, which means that 48% of it is the empty space in between the spheres. Any questions on the procedure we just went through to find this information? Did you see geometrically what it is we're trying to do? Okay. So the general idea is that when you're looking at a solid and you're trying to maximize its fractions, the closer things are together, that corresponds similarly to the less empty space you have in the structure, then typically the greater the fractions are. Yes? Okay, so in this case, this isn't necessarily a molecule. So usually when we're first introducing this, we're doing this and talking about metals. Okay, so I think if I'm remembering correctly, the polonium, it might be the only metal that actually crystallizes using this simple cubic structure. So each one of these would be a polonium atom. But if you've watched the properties of solids video, the model we use for a metal is not individual molecules. It's an electron C model, where you have the cores of the atoms in whatever crystal structure they're in, with a sea of electrons that are shared amongst them all the way across it. Okay. In the next unit cell that's over. So what we're doing is we are identifying here the smallest repeat unit, and there can be something that once. So this atom at the corner here is in 8 separate unit cells that are nearby. This one is in 8 separate unit cells, which share some of the same ones this one has. Okay. So it's kind of like if you have a house that has a wall separating 2 rooms. You ask yourself, well, which room is the wall in? Well, that's in both. Half of it's in each of the two rooms. Okay, so the reason we care about this is that the density of the materials is affected by the packing density that you have, and when you start to add things into the structure. So if, for example, you start looking at ionic compounds, you'll have one set of ions forming one crystal structure, and then you'll have the other ions filling in the gaps, filling in little holes. And so knowing how big the holes are can tell you how big of an ion you can put in that crystal structure. Yes? I'm unfortunately having trouble hearing you. The 6, oh, where did this come from? The 6 came from there being a 1/3 in the numerator, which is just like multiplying by 1/3 here, and so the 3 times the 2. Okay. Okay. Any further questions on hacking efficiency? And naturally, for each different crystal structure, you're going to have a different calculation for this, because if you're doing body-centered cubic, then it's the body diagonal where the atoms are in contact with each other. And for face-centered cubic, it's going to be the face diagonal that's going to have the atoms touching each other. So, but I wouldn't go through trying to memorize those things. Try to be able to visualize the geometry, and then the calculation's pretty simple. Once you hear it, you just maybe use better in the theorem of time or two once you know some diagonals. Yes. Sure. In fact, I'm going to switch to this and here. Okay, so there's a question earlier about how many unit cells there are in a system or in a molecule. The idea is that it probably extends pseudo-infinitely in each direction on the side in terms of the size of the structure. So this one shown here in the upper left is simple cubic. Body-centered cubic is where you put another atom in the center of the body. Okay. Face-centered cubic is where, instead of putting one in the center of the body, you put one in the center of each face. All right. I'm going to go down here for a second. And so the issue here is that for body-centered cubic, in order to have room for the sphere that you are putting here in the middle, you have to expand the lattice a little bit. You have to expand the corners away from each other so that they are no longer directly touching along the edge. And so the way they are touching is across the body diagonal, across opposite corners of the cube. And can you see that? Okay. And then the face-centered cubic, this is this one. We are again expanding the lattice, and we're putting a new atom in the center of each face. And so the the atoms that are in contact with each other are along the diagonal of a face. So the diagonal of a face here is going to be 4 atomic radii. And experimentally, there are some techniques we can use, X-ray diffraction and electron diffraction in particular, that will directly let us measure the side lengths of unit cells. And so from that, and knowing which crystal lattice we are using, if it's face-centered cubic, we find the size of a unit cell is X. We can then use geometry to determine the radius of a molecule, or excuse me, of an atom. And direct ways to measure the size of an atom this way. And does that help? So any further questions on patching efficiency or on yes, coordination number, yes. So that was the next thing we were going to get to. So coordination number is the question of how many nearest neighbors are there to each atom. So I'm going to share again. So let's come up here and look at simple cubic. So if we look at this central atom right here, it's not central in the unit cell because there is no central atom in the unit cell, but it's center of this extended version that we've drawn. We can count up how many nearest neighbors there are. 1, 2, 3, 4, 5, 6. That's it. That's the coordination number. Okay. We can tell that this one is further away from this one than this one is. So because it's across the diagonal of a face rather than along the edge of the face. So this is going to be square root of 2 times that length from geometry. So the number of nearest neighbors in this case is 6. So for a simple cubic lattice, the coordination number is 6. If we look at body-centered cubic, well, if we focus on the red atom, then pretty clearly all of the 8 corners are equidistant from that central atom, and everything else is going to be further away than that. So our coordination number for body-centered cubic is 8. Now you can raise the question, that's if you're looking at the central one, but if you're looking at the corner instead, that's going to be hard to visualize. Well, I go through a visualization here, where if we take one unit cell of the body-centered cubic, we'll extend it in each direction a little bit, and now let's redefine our unit cell so that it's on the red atoms instead of on the gray atoms. And then take away the excess that's on the outside. This is still body-centered cubic, just with the red and gray swapped. So the coordination number for the gray atoms is identical to the coordination number of the red atoms. Then if we look at face-centered cubic, this one's a little harder to do. So let's focus on this red one that we have in front. Now, pretty clearly, it's in contact with these other red ones and these gray ones here, but not with the far corners that we have. So I'm going to color that one blue and then take away the ones that it's not in contact with. But now it's also in contact with some that are in the next cell over, like this. So this now has a coordination number of 4, 8, 12. Now, why do we care about coordination number? Well, the main reason we would care about coordination number is that there can be nearest neighbor interactions between things. If you get into, say, the quantum mechanics of solids later on, then you can have maybe charge transfer or charge jumping from one to its next neighbor or so on. You can have reactions of various kinds starting to happen amongst those. And knowing how many it can react with tells you something about a comparison of the interactions. We're not going to get into those details, but being exposed to the idea of a coordination number sets you up for that once you get to that in other classes. Any questions on coordination number? Okay. Let me switch back. Okay. How how are FCC and which is space center qubit and qubit close packing the same? Okay, I guess I shouldn't have stopped sharing this yet. So that one, a little harder to visualize. So we're looking at space center qubit. We're rotating a little bit, and we're going to recolor it now into layers. We're going to take off some of the top layers. So the arrangement that you see here is what you would get basically stacking oranges in the grocery store. You take a set of spheres and you pack them together as closely as you can, and you form this sort of triangular or hexagonal kind of arrangement. This is a really cool experiment you can do by yourself. Pick up 20 or 30 coins for the same value. Doesn't matter if they're dimes, pennies, quarters, whatever, but they need to be the same. Spread them out on the tabletop and just bring your fingers to it and just push them together so that not trying to squeeze from the sides, but just push them along as though you're sort of sweeping them towards the edge of the table. And what you'll find is that they will naturally collect into this same kind of layer arrangement where you have this sort of hexagonal arrangement of the coins. And that's simply because it minimizes the extra space. It maximizes the contact between all of the coins. When you have this kind of arrangement of spheres, what you're doing to start the next layer of oranges or the next layer of atoms, is you're putting these spheres down into some of the holes that are formed by a triangle down below it. But you can't fill all of them. You notice that this hole in the green layer is covered, this hole in the green layer is not. Right? Which means that, what we've shown so far is that this space-centered qubit arrangement, when you turn it on its corner and look at it, you get this layered kind of arrangement, which is the closest arrangement you can get, so we call it qubit closest packing. But once we get past 2 layers and start to the 3rd layer, we have a choice. We can put the 3rd layer over the holes that are in both the green and the red layer, or we can put them over the original holes we had, over the original atoms we had in this case, in the green layer. Now, the packing density is identical in these cases because as you add each layer, they are nestling down into the gaps in the previous layer exactly the same. The difference is just in the arrangement of them, because here in the right-hand side, you have a lot of the empty spaces lined up in a row. In this case, the empty spaces are offset from each other. Same amount of empty space, just shifted. Does that help with the visualization of these? This right-hand one, okay, so here we call this an ABC arrangement because we go green, red, blue, green, red, blue, green, red, blue. In this case, we go green, red, green, red, green, red in an AB arrangement, which is hexagonal closest packing. And so that is the one example of a unit cell we're looking at in this class where it does not, when you rotate it around, it does not have a unit cell that is qubit. Okay. All right, the last question we had was about from the content video. I mentioned the Cullinan diamond, which was 1.33 pounds. And how many carbon atoms were in this one molecule? A lot, yes. So, but there was a question here, how do you even set up this kind of problem? So, this is just going to be straight dimensional analysis. Yes? Okay, so we know we have 1.33 pounds. And you're going to have some kind of conversion factor, because we don't like using pounds in chemistry. You have some kind of conversion factor from pounds to grams. Okay. I'm going to assume that you can look that up. Okay. Pounds are going to cancel. Once you have grams, you can say, okay, and remember this is carbon, pounds of carbon. So you can have grams of carbon to moles of carbon using the molar mass. All right, molar mass of carbon. That's going to cancel, and you're going to have moles of carbon. You're then going to multiply this by Avogadro's number. So 6.022 times 10 to the 23rd atoms, carbon, per 1 mole of carbon. Okay. And that is going to give you your answer. So mole of carbon cancels with mole of carbon, and so you're left with atoms of carbon. I'm going to assume that you can figure out the, you can look at the conversion from grams to pounds, and I assume you can look at the molar mass of carbon. And so you're going to get some big number. It's going to be, I think it's 3 times 10 to the something. And what I'm asking you for in the quiz is what that something. 3 times 10 to the what? It's going to be big. And the point of that particular question is that the diamond structure itself is a carbon atom covalently bonded to another carbon atom, covalently bonded to another carbon atom, going off seemingly endlessly in all 3 dimensions. So it is, in a very real sense, this one diamond is a single molecule. It's what's known as a network solid. And the covalent bonds are an unbroken chain from one side of the diamond to the other side, which makes it very, very different in terms of properties than any molecule you're used to dealing with. And this is why diamond is one of the strongest materials around, because you're dealing with covalent bonds when you're trying to do something with the defined. Okay, I have gone through all of the muddiest points that came up. We have a few minutes left. I am happy to answer any other questions from the audience or from the chat.
So wondering if the PowerPoint with all the models.
Well, the PowerPoint with all the models and stuff, that one is what I use to make the video. So it's there with all that stuff. The PowerPoint itself has all these various animations and stuff in it, which make it very hard to view as you're going through it. So honestly, it's easier for you to just go look at the video. Yes.
I don't think it's about last week,
Okay. So the question was, on the last week's supplementary problem, do you just look at the central atom to figure things out? So what you have to do is go through and catalog all of the intermolecular forces that are present in the molecule overall. Now, it turns out that from the perspective of determining if you have a dipole moment, what matters is the nitrogen and what it's attached to. So analyzing the dipole moment around the nitrogen is the correct thing to do. But you do have to look at the other atoms as well to say, do I have hydrogen bonding or not? What can I determine about, are they the same atoms so that I know that the dispersion forces might be the same, those sorts of things. But it really does take the process of going through and making sure you have cataloged all of the intermolecular forces that are present in each of them. In cases where they're the same, it doesn't affect it. In cases where they're both present, but they may be different in magnitude for some reason, then that's part of the explanation, and so on. Anything else? We have about 3 or 4 minutes. Okay, not hearing anything. So thank you all, and start thinking about the group activities. And somebody, if you can get back to me and let me know if the group discussion boards are visible or not. I think I got that set up right. If I didn't, I need to know so that you guys can talk to each other. Okay.
Like, I don't know how to figure out whether it's going to be stronger because it's not a hydrogen bomb because it does different things.
Well, so in this case, there is no hydrogen bonding because none of the hydrogens are attached to the nitrogen. In both of these cases, there are hydrogens that are attached to the nitrogen. So this can be a hydrogen bond donor, this can be a hydrogen bond acceptor. So you're going to have hydrogen bonding in both.
There is hydrogen bond here, even though it's not present right now.
So remember that hydrogen bonding is between 2 molecules of synchron. So this donor can then attach to this acceptor on the next molecule over.
Oh, okay. So this H is attached to something else.
No. So if you have nitrogen, carbon, hydrogen, and then on the next molecule you have nitrogen, hydrogen, carbon, then this right here is the hydrogen bond.
So it's not that it has a hydrogen bond, it's that it has a potential.
That's right.
Hydrogen bond?
That's right. And for a hydrogen bond to form, you need a donor and you need an acceptor, which is the lone pair.
Okay. So if you just see that, you know it's going to.
Yes, that's correct.
So for example, my question, do we
It's going to be percent-wise. I have a rubric that I'm using for each of the various points, and that rubric should become visible once I do the grading. Unfortunately, I was catching up on all the group assignment stuff, so I haven't graded yet, but I will hopefully do that in the next year.
And then with the content videos, I have a feeling that like this, the collisions, it won't let me attempt it more than twice.
Okay, so
like I watched it all the way through twice, and then I wait to watch it a third time, and the quizzes don't show up.
So if that happens to you, send me a message privately telling me that you want me to delete the unfinished attempt, and then that will reset it for you so you can go back.
And then it's that on the ones that went through last week too, but they were already used.
So tell me about it. I'll go back and remove that attempt, and you should be able to do it again.
Okay, thank you.
That's a weird, like, so hot water has the